Hey everybody, Mr. Caldwell here. Wanted to give you a quick little help video on introduction to charge, and it's really the underpinning. It's the thing that makes static electricity things happen. And in order to understand why static electricity things happen, it's shocking, yeah, pun intended, that you have to go back and think about some basic chemistry. And in chemistry, we should have learned, hopefully, that there were three particles. There's the protons and the electrons and the neutrons that make up an atom. And the protons are positive, right? The electrons are the negative particle, and the neutrons have no charge, right? Uh, so please keep that in mind as you're thinking about static electricity things. Now, we also have to go back and remember sort of what does the atom look like? Now, this is a gross oversimplification of what the atom looks like, but at the end of the day, you'll notice that the purples, the positives, those are the protons, and the orange, the neutrons, the neutrals, those all seem to be bunched together in the middle, and they live in that thing called the nucleus. And that's great, super important to remember. But the most important thing for static electricity is the electrons, because the electrons are sort of like the introduction to an atom. When one atom encounters another atom, the first parts of the atoms that are going to touch, that are going to interact with one another, are going to be the electrons. It's like the outermost layer. So that's why these electrons are out here. They're actually in orbitals, and it's a little complicated. So we're just going to draw a picture to make it simple and pretend like they're little planets orbiting the sun. They're the things going around this dense, centrally located nucleus. And that nucleus, the things that are in the nucleus, the protons and the neutrons, they're very happy there. They don't want to go anywhere, but the electrons, they have freedom, all right? They're outside there. And so what I've got down here is just a little sort of accounting, right? So since the protons are positive, and I have 1, 2, 3, 4, 5, 6 of them, the 6 protons by themselves give this particular atom a charge of positive 6, right? Because each proton has a charge of what we call just positive 1. And then if you count, I've got 1, 2, 3, 4, 5, 6 green electrons. So I also have a negative 6 associated with the fact that this atom has 6 electrons. And the story of the charge for an individual atom is really pretty straightforward. You look at and we can look at the number of neutrons, but neutrons have no charge, so we don't care about that. So if I wanted to figure out the total overall charge on this, I would take the plus 6 from the 6 protons and the minus 6 from the 6 negative electrons. A positive 6 and a negative 6 gives us 0. And so if I ever want to find the total overall charge on just a given atom, I take the number of protons and I add the number of electrons. So that's just a quick review of the idea of charge in an individual atom. Now let's expand that just a little bit. So something to keep in mind here is that when we're talking about anything that has to do with static electricity, the only charge that's free to move, okay, the only things that can move are these negative electrons. Sometimes atoms can gain electrons, sometimes atoms can lose electrons. Protons and neutrons, they stay home. They are trapped in that nucleus. They can't go anywhere. And so when we are talking about static electricity phenomenon, remember that protons and neutrons don't go anywhere. Everything that is going on in static electricity has to do with moving electrons. So let me go ahead and switch over here, and I'm going to share a little bit of a different thing with you, right? And you may or may not have already seen this. You may be seeing it sometime soon, but hopefully now you're looking at a screen that has, looks like a nice warm sweater and a balloon and a wall. And so the nice thing about this simulation is it drives home the idea that I just said, hey, we've got these protons, neutrons, electrons. Neutrons aren't even shown here because remember, neutrons have no charge, all right? Neutron goes into the bar, asks the bartender for a drink, and the bartender looks at the neutron and says, hey, for you, no charge. You get it? That's a joke. All right. So what we're going to do is we're going to take the balloon, which you'll notice has an equal number of positives and negatives. So if you think about that, that means that it has a +4 and a -4. So the total overall charge on the balloon has to be 0 right now. And it looks like the total overall charge on everything, the sweater, the wall. So everything has a balance of charge. Same number of charges, it's neutral. Watch what happens when I take the balloon and I put it near the wall. Exciting, right? No, not at all. Nothing happened because it's a neutral object and a neutral object. Neutral objects, nobody has too many electrons, nobody has too few electrons, no electrons have moved. Boring. But when you take an object and rub it against another object, some objects are better at attracting electrons than others. So what I'm going to see here is, oh my goodness gracious, that's insanity. Do you see what is happening here? That balloon appears to be an electron thief. As I rub the balloon over the sweater, okay, the balloon has what we call a greater electron affinity. If you have an affinity for something, you have a liking for it. So the balloon really likes electrons. In fact, it's a better electron attractor than the sweater. So the balloon says, hey, sweater, you don't get those electrons anymore. I'm going to take them. And so what we'll notice is that goodness gracious, I now have a balloon that has way more electrons than protons. So overall, the balloon now has what charge? It's got to be negative. And now the sweater, which used to have a bunch of electrons and protons, now has lost electrons. So because it has lost those electrons, its overall charge is positive. And one of the other things that you'll learn here in this unit is that opposite charges do what? They attract. So when I release the balloon, when I let go of the mouse, the balloon is attracted to the sweater. Now, there's all kinds of cool things that come from this. But at the end of the day, that is the essence of static electricity phenomenon. One thing has more electrons than the other. So you have an imbalance of charge, right? Especially if you have something that's positive and something that's negative, they're going to attract. So let me go ahead and stop sharing my screen there. And I'm going to go back and I just want to do one last little math thing with you if I can. All right. So let's see if I can get my computer to cooperate. All right. So let's imagine that we have a scenario where we have two objects, right? Object 1 and object 2. And these two objects to begin with are neutral, right? And remember what that means. That means that they have, it doesn't mean that they have no electrons or no protons, because neutral, no charge. Neutral means a balance in charge, right? So let's say that these are initially both neutral. And we rub these two objects together, and just like we saw with the balloon and the sweater, there's an exchange of charge, all right? And so let's say that object 1, so we rub these things together, right? And object 1, right, gains electrons, and object 2 loses electrons. Well, if I asked you what's the charge on them, all you could say is, well, if this one gains electrons, you have to really sort of switch your thinking. Even though it's gaining, you're like, oh, gaining is good. Gaining is positive. No, what charge do the electrons have? Electrons are negative. So if I give you a bunch of negative things, you are going to end up being negatively charged. This one who lost electrons lost a bunch of the negatives, so now it has more positives than negatives, so it's going to be overall positive, all right? Now, we can add something to this. Charge is measured in coulombs. And I don't want to get too far into it because I want to try and wrap this video up. Charge is measured in this unit that's called a coulomb. Coulomb was a old French dude. So if charge is measured in coulombs, all right, that means protons have a certain amount of charge, and that's going to be a positive. Electrons have the exact same charge. It's just that it's a negative sign in front of that number. So let's just say that if this one is gaining electrons, all right, let's say that it is gaining, I don't know. Let's say that there's an exchange of charge of, we'll say 3,000 coulombs, okay? So if this one gains electrons to the tune of 3,000 coulombs, then its charge would be negative 3,000 C. C is the symbol for coulombs, right? And this one would be losing 3,000 electrons, right? So it's going to end up being a positive 3,000 C. But if you'll look back at this, remember how we said these were neutral? So guess what number would have been associated with neutral? 0C, all right? Because the number of protons and electrons would have been equal, all right, in each of these critters, all right? And if you need a little bit more of a concrete example than that, all right, let's imagine that I have proton, electron, proton, electron here on object 1, and I have proton, electron, proton, electron, proton, electron here on object 2. All right, and so we rub them together. And let's say that there is object 1 loses 1 electron, all right? So then this would be our before picture. And so our after picture, it's going to be pretty straightforward. We rub these guys together. This picture is now going to have the positive and a negative and just the positive because it lost 1 of its electrons. This guy, object 2 over here, and remember why we're not drawing the neutrons. Neutrons have no charge, so they're totally not interesting. And so I've got not only what I originally had, my 3 protons and my 3 electrons, right? But now I have to put a little negative charge in here because it gained the 1 electron off of object 1. So this is object 2. So if I had to say, all right, what is the charge on this? This is now going to be +1, and this is going to be -1, but we're not going to use Coulomb because it turns out that an individual electron has a very, very, very tiny amount of charge. 1 electron is 1.6 times 10 to the negative 19th Coulomb. Now, I'm not going to get into this too much right now, but 10 to the negative 19th is a wicked tiny number. It's like 0.000000. There's lots of zeros there, and then eventually at the end there's a 1/6. And because an electron is negative, we remember that that's a negative 1.6. So if I wanted to actually write the true honest to gosh answer, because +1 -1, that's a little bit of an oversimplification. This would be plus 1.6 times 10 to the negative 19th Coulomb. And this would be minus 1.6 times 10 to the negative 19th Coulomb. That is a lot more than I was hoping to get done here when I originally sat down to make this video, but I'm hopeful that it helps you in understanding what's going on. And so with that, I'm going to try and figure out how to stop recording this. All righty. Thanks, guys, and good luck to you. See you soon.